Hi, my name is Ram, and I'd like to go over strongly connected components. And the idea is that if you have a larger graph, there are areas within that larger graph that can be identified as being a strongly connected component, where if you're looking at a particular node, then you can reach another node in that particular subgraph, and you can in fact go back as well. So we see that property played out here if we're looking at, let's say, C and D and F and G, because if I'm on F, I can go to G, and if I'm on G, I can go to F. And that is true also for C and D. Now, that's also true for A, B, and E, because if I'm on B, I can go to E. If I'm on E, I can go to A, and I can reach every node from every other node. That's a good heuristic for trying to understand what a strongly connected component is. Now, really the core goal here is to be able to count how many strongly connected components you have. And so what we end up doing is we end up creating these boundary points between a strongly connected component, but we actually don't know what those boundary points are in advance. I mean, this is just a visual diagram to illustrate that there are boundary points, but what we want to do, or rather what the end goal is in fact to be able to create these boundary points. So here, if I look at essentially what the technique is to count these graphs, what you do is you recognize two things: that if you're on a source strongly connected component and you do a DFS, you're always going to end up in a particular segment of the graph, which in this case is component C3, which is represented as a condensed graph. And that helps because it tells us where the DFS would end. But really, the core problem is that we're in these connected components and we end up trickling out. So if we reverse if we do what's something called a transpose of a graph, we reverse the edges so that now you're not leaving a particular component, then you're trapped in a component. And then when you run DFS again, or really any graph traversal algorithm, you can then count how many traversals you did that were stuck in a particular confine or trap. And so that's what we have here. And like I said, being trapped in the end node is one very important realization to have, because that's what allows you to confine particular traps. And if you do that right after your initial DFS, you'll recognize that the DFS of the largest finish time is in fact in the source component. And again, that helps. And naturally, at the end of the day, if you'd have ran DFS on each connected component, because each component is now a sink in itself, you'll have a certain count, which will represent how many strongly connected components you have.